this week we'll be focusing on classifying word problems based on their unknowns. Last week we learned that addition and subtraction problems are classified based on the types of actions or relationships described in the problem. We also learned that these problem types correspond with the ways that children think about the problem rather than how adults think in terms of operations. Last week, we started thinking about word problems using this flowchart. When we examine a problem, we decided, is the quantity changing? Is there action? Or is the quantity in the problem not changing? Is there a relationship? If the quantity was changing, we know that it's a join problem if the quantity increases, or a separate problem if the quantity decreases. We also know that if there is a relationship in the word problem, the problem is a part-part whole if it talks about a relationship between a set and its subsets, or a comparison problem if it compares the two quantities. This week's learning will build on these ideas. We're going to be building on that flow chart this week to look at the specific problem types within each area. For example, we've been talking about quantity changing problems where the quantity increases, aka join problems. You'll notice in this chart highlighted in pink that there are actually 3 types of join problems. There are join result unknown, join change unknown, and join start unknown. Likewise, there are 3 types of each of the problem types we looked at last week. The rest of this video will focus on digging deeper into these specific problem types and helping you distinguish between each one. Let's look a little deeper at this chart. I'm going to start on the left side where the 4 problem types we already know are written. You'll notice that by the word join, you'll also see the word add to, and by separate, take from. Join and separate is language used by one particular group of researchers and publishing companies, and the add to, take from language is used by a different set of researchers and textbook companies. And so I wanted to be sure that you are familiar with both of the languages. Similarly, part-part whole word problems are sometimes referred to as put together, take apart. However, everyone seems to be consistent with the comparison problem and calling them compare or comparison. As we look at this chart, again, I've divided it into 2 colors to help you distinguish between the quantities that are changing word problems and the quantities that are not changing word problems. As you examine this chart, you probably notice the little letters and numbers in the bottom right-hand corner. These letters and numbers indicate the grade level that each problem type is expected to be mastered. So for example, if I am teaching kindergarten, my students are expected to master join result unknown word problems, separate result unknown word problems, part-part whole total unknown word problems, and part-part whole both parts unknown word problems. Mastering these problem types means that in all future grade levels, students are expected to be able to solve problems within those structures. So as students move through the grades, in first grade, they'll solve the same problem types, but the numbers will get bigger. Then in first grade, they start to learn new problem types like join, change unknown, separate, change unknown, part-part whole, one part unknown, and the comparison difference unknown word problem. These same addition and subtraction word problem type structures are also used as students move into learning about fractions in grades 3 through 5. These same structures are used, however, fractions are inserted in the place of the whole numbers. Likewise, we use the same problems for decimals as well. You're probably wondering about those little equations that are written under the action word problems. We'll take a moment to talk about those. Those equations are known as semantic equations. Semantic equations align perfectly with the action that's happening in the word problem. Let's take a moment to look specifically at the semantic equations in the join row. The first problem in the join row says, 2 bunnies sat on the grass. 3 more bunnies hopped over to them. How many bunnies are on the grass now? If I were to write an equation that perfectly matches that situation, I would write this equation. 2 plus 3 equals blank. That is the semantic equation for this problem type. The semantic equation helps us determine the problem type. We already know that this is a join problem because the quantity is increasing, but this specific problem type is known as join result unknown because when we write the semantic equation, it's the result that's unknown. Let's look at the second problem. 2 bunnies were sitting on the grass. Some more bunnies hopped over to them. Then there were 5 bunnies. How many bunnies hopped over to them? If I were to write an equation that perfectly matches this problem situation, I would write 2 plus blank equals 5. Notice how this connects with the word problem. 2 bunnies were sitting on the grass. Some more bunnies hopped over to them. Then there were 5. We call this problem type join change unknown. We know it's a join word problem because the quantity is increasing. We call this change unknown because the unknown is the change. In other words, how many more bunnies hopped over to them. Let's look at this final joining word problem. Some bunnies were sitting on the grass. 3 more bunnies hopped over to them. Then there were 5 bunnies. How many bunnies were on the grass first? An equation that would match that, the semantic equation, would be blank plus 3 equals 5. Some bunnies were sitting on the grass. 3 more bunnies hopped over to them, and then there were 5. We call this a join start unknown word problem because there's a joining situation and it's the start that's missing. Looking back at this chart again, we just explored each of these join problem types. We looked at the join result unknown, the join change unknown, and the join start unknown. If we notice that there's a separating situation, we also use a semantic equation to represent that situation and how children think about that problem. We'll look at this last one as an example. Some apples were on the table. I ate 2 of them. Now there are 3 apples. How many apples were on the table to start? Notice the semantic equation is blank. Some apples were on the table. I ate 2 minus 2. Now there are 3 equals 3. This particular problem type is known as the separate start unknown. Students are introduced to each of these problem types at a different grade level. Looking at the chart, you'll notice that in kindergarten, children are introduced to result unknown word problems, both join and separate situations. In first grade, we introduce students to the change unknown word problems, both join and separate. But in first grade, children are also responsible for result unknown word problems. In second grade, we introduce students to the start unknown join and separate word problems, but they're also required to still understand change unknown and result unknown word problems. As teachers, we need to be able to distinguish between these problem types so that we can write appropriate problems for our students at each grade level. So, just to recap, when we're thinking about these action problems where the quantity is changing, we can use semantic equations to help understand the problem type. These semantic equations represent how children think about each of these word problems, and their problem-solving strategies are going to be connected with how they think about the word problems. When you encounter an action word problem where the quantity is changing, write a semantic equation. This will help you determine the problem type. Semantic equations are a great tool for representing word problems with action, like join and separate. But when it comes to problems where the quantity is not changing, that they're based on relationships, it's easiest to create bar models to represent these situations. You'll notice in these quantities not changing word problems that I've given you a bar model to represent each of the situations. In a bar model, a bar is used to represent a quantity. Let's look at the bar models to represent part-part-whole problems. You may have actually used a part-part-whole model in the past, but often we use this model flexibly and also use it to represent join and separate problems types. Some of you actually talked about this in your small group last week, and it can make it a bit confusing. Remember, when we're thinking about problem types and we use bar models only to represent the quantities that are not changing. So let's look at this first bar model. 3 red apples and 2 green apples are on the table. How many apples are on the table? Notice in this problem, I know the 2 parts, the 3 and the 2, but I don't know the whole. Let's look at this very last problem type. It's called a part-part whole, both parts or both addends unknown. This is actually a kindergarten type. Grandma has 5 flowers. How many flowers can she put in a red vase, and how many flowers can she put in her blue vase? Notice in this problem they only give us the whole, and the 2 parts are unknown, hence the name, both parts unknown. This problem actually has multiple solutions, and in kindergarten we do expect students to find all the solutions to this problem. When I am creating bar models to represent comparison problems, I create a shorter bar and a longer bar. Also in these comparison problems, there is a difference. The difference is represented by the little number or the question mark that's kind of hanging out there by itself at the end. Let me give you an example. Lucy has 2 apples and Julie has 5 apples. How many more apples does Julie have than Lucy? So when I think about this problem, I know the 2 quantities. I know the larger quantity is 5, and I know the smaller quantity is 2. What I'm trying to determine is the difference in those quantities. I represent this with a question mark outside the bar. When we're talking about comparison problems, there's actually 2 versions of the problem. There's a how many more version and a how many less version. Interestingly, the solution in both versions of the problem is the same, but the wording is a bit different. For example, in the first problem, it asks, how many more apples does Julie have than Lucy? But in the less version, we ask, how many fewer problems does Lucy have than Julie? So the bar model is the same, the solution's the same. What changes is just the language in the question. Let's look at these last 2 comparison problem types, bigger quantity unknown and smaller quantity unknown. These problem types align perfectly with the bar model. If you look at the bar model in this problem, the bigger quantity unknown, you'll notice that it's the bigger bar that we don't know yet. In the smaller quantity unknown, it's the smaller bar that we don't know yet. Let's read the problem. Julie has 3 more apples than Lucy. Lucy has 2 apples. So I put Lucy's 2 apples in the bar. I put the 3 more outside here. And the question is asking, how many apples does Julie have? That's the question mark. And Julie is the larger quantity. So that's why it is called a bigger quantity unknown comparison problem. Let's look at the smaller quantity unknown comparison problem. This one says Julie has 3 more apples than Lucy. So that means Lucy has the smallest amount and Julie has 3 more. Julie has 5 apples. Here's my 5. How many apples does Lucy have? In this problem, Lucy is the smaller quantity and her quantity of apples is the unknown. I'm guessing your brain's probably pretty full right now. Mine is too. Just for a quick recap, last week we talked about classifying word problems based on their structure or the relationships within the problem. When we look at a word problem, first we need to determine if the quantity is changing. Is there action, or is the quantity not changing? Is there a relationship? If there is action, we know that the word problem must be a join or separate. And for those types of word problems, we use semantic equations to classify those problems because those semantic equations align with how children think. If the problem has no action, the quantity is not changing, it's about a relationship, then we use a part-part whole or comparison model. We call the part-part whole and comparison models bar models because they're created by using bars to represent the situation. I know there's a lot of new things to consider here. We'll be working on this all week. And if you need my help, please reach out through email and I'll be glad to set up a time to meet with you virtually or hop into your small group, or I can even just email to support you. I'm here to help. Reach out.